Have you ever stopped to think about what's happening inside your phone or computer? I mean, really think about it. Everything you do, sending a text, streaming a movie, even the most mind-blowing AI, it all boils down to just two numbers, 0 and 1. It sounds kind of impossible, right? But that simple code is the secret language of all modern tech. So let's pull back the curtain and see how it really works.
So that's the big question, isn't it? How in the world can two tiny digits, a simple on or off, create the incredibly rich digital world we live in? Well, we're going to break down that secret language piece by piece.
All right, first things first. Before you can speak a language, you need to know the alphabet. And for a computer, that alphabet only has two letters, 0 and 1. This is called the binary number system, or base 2. Think of it like this. We humans use 10 digits, 0 through 9, to write out any number we can possibly imagine. A computer does the exact same thing, but it only uses 2. That's it. Every single piece of information, a number, a letter, a pixel in a photo, it's all just a long, unique string of these zeros and ones. Okay, so if computers have an alphabet, they've got to have some rules, some grammar, right? For a computer, that grammar is math. But how do you actually do math when you can only use a 0 and a 1? It's actually simpler than you might think. You know, binary addition is actually guided by just 4 super simple rules. 0 plus 0 is 0. Easy. 0 plus 1 is 1, no problem. The only one that's a little tricky is the last one, 1 plus 1. In our world, that's 2, but in binary, you write 2 as 1, 0. So the result in that column is 0, and you carry a 1 over to the next column. It's literally the same carry the 1 you learned in grade school. Let's see this in action. It'll make more sense. So we're adding 1, 1 plus 1. Let's start on the right. 1 plus 1 gives us 0, and we carry that 1 over to the next column. Now in that middle column, we've got another 1 plus 1 situation, so same deal, we get a 0 and we carry another 1. That final carry just drops down, and boom, there's our answer, 1, 0, 0. It's this exact simple logic just repeated millions of times a second that powers every single calculation. Okay, so addition seems pretty straightforward, but what about subtraction? Or how about just the idea of a negative number? I mean, how do you represent less than 0 when all you have are on and off switches? This is where computers get really, really clever. The first step in this clever little trick is something called the ones complement. And it's shockingly simple. You just take your binary number and you flip every single bit. That's it. All the ones become zeros and all the zeros become ones. You can see it right here. The binary number at the top gets completely inverted to create its ones complement down at the bottom. It's just a direct one-for-one flip. But this is only the first part of the solution. The method most computers actually use is called 2's complement, and it's a super simple two-step recipe. First, you do exactly what we just saw. You find the ones complement by flipping all the bits. And then, for step 2, you just add 1 to that result. That is the whole magic trick. Flip and add 1.
So, why? Why do all this? What is the point of this flip and add trick? Well, it all comes down to this simple mathematical truth. You see, computers are designed to be as simple and efficient as possible, and it's way easier to build circuits that only know how to do one thing, add. By using 2's complement, a computer can magically turn every subtraction problem into an addition problem. It just adds a negative number. It's a brilliant, brilliant simplification.
So now that we kind of get how computers think about numbers, let's talk about how they store them. And this is where we have to make a really important distinction between an idea and, its physical form. A number is just an abstract concept, right? The idea of 10 is the same whether you write it as 10, or the Roman numeral X, or even the word 10. But data is the physical thing itself. It's the raw sequence of bits and bytes sitting on your hard drive, and that data on its own has no meaning. It's just a bunch of marks until someone or some program decides how to read it.
And this is where a huge problem starts. Thankfully, pretty much all computers agree on what a single byte is. It's a group of 8 bits. But for numbers that are too big to fit in just one byte, a major disagreement pops up about which end of the number you should write down first.
And this leads us to one of the most fundamental, classic arguments in the history of computing, the Great Byte Debate, also known as the endianness problem. Honestly, it's just a simple difference in convention, kind of like how some languages are written left to right and others are written right to left.
A big-endian system stores the most significant part, or the big end, of a number first. A little-endian system does the exact opposite, storing the least significant or little end first.
Now, this disagreement leads to the really famous Nuxie problem. Let's say a big endian machine stores the word Unix in memory. It stores U, then N, I, then X. Makes sense. But if a little endian machine comes along and reads that exact same memory, it sees N, then U, X, then I. It reads Nuxie. The exact same data is interpreted as complete gibberish. And this is a massive problem when different computers need to talk to each other. So how do we fix this chaos? Well, two main solutions emerged. The first is called network order. Basically, everyone agrees that when you send data over a network, you convert it into a standard format, big endian first. The second solution is a byte order mark, or a BOM. This is like a special little magic number you put at the very beginning of a file. If the computer on the other end reads it backwards, it immediately knows, this file was written in the opposite style, I need to swap all the bytes. Pretty clever. Now I know, all of this might seem incredibly low-level, super abstract stuff, but these fundamental rules, they are the absolute bedrock that our entire digital world is built on. Understanding binary is absolutely crucial in digital electronics. It defines how the logic gates in every single chip work. It's essential for programmers working close to the hardware. In data science, it lets people encode huge data sets efficiently. And in networking, those solutions to the endian problem are the reason an Apple computer and a Windows PC can seamlessly share information over the internet. So at the end of the day, our whole digital universe, from the simplest pocket calculator to the most powerful supercomputer, is all built on this incredibly simple foundation of just zeros and ones. It's an amazing testament to how powerful simple rules can be when you apply them at a massive scale. But it does leave us with one last big question. As our data and our problems get infinitely more complex, will this simple binary foundation be enough to carry us into the future?